All right, guys, let's start. Okay. So now we are in the second lesson, right? Second lesson is root finding algorithms. Even though I explained you a little bit about root finding algorithms in your uh, previous lecture, right? But here we'll go deeper, right? We'll go deeper and try to understand each and everything about root finding algorithm. We're still doing your introduction to numerical method in finance, so you're still just starting up, right? Just starting up in your numerical methods, which is a new topic. But now we're focus, right? The focus will shift to your root finding algorithms, right? So the bigger picture here is that whenever uh, we look at tough financial concepts, right? One of the most important things which comes to our mind is that whether a particular thing has a closed form solution or numerical solution, right? Because if it has a closed form solution, things are very easy, right? But most of the thing doesn't have your closed form solution, right? We have to rely upon numerical solution because as we kind of progress in advanced level of confidence, we realize that it's not that simple that everything can be solved by just putting the formula, right? Sometimes we have to do approximation, sometimes we have to use computer methods, sometimes we have to use other mathematical operations to reach the value. And in this whole process, right, in this whole process, what happens sometimes is that we get certain kind of errors, right? So because when we are kind of converting these equations, these formulas, these numbers, right, into your language of computer, right? There are certain chances that we get certain errors, and those errors has to be understood properly. That's why we did our error analysis earlier. That's why when we were solving things in the previous chapter, we realized that we have to focus more on your relative error analysis rather than your absolute error analysis, right? So that's the background. So keep that background in mind, right? Because as we progress, you will realize that all these methods have a kind of approximation, right? And now we are starting with one of the most basic and one of the most simplest method called root finding algorithm. But there is increased dependency on your approximations and algorithms so that we are able to solve this difficult quant finance application which doesn't have closed form solution, right? So that is what we have, right? So big picture overall is that root finding means find the value of that which makes a function equal to 0. So f of x equals 0. In finance, we often know the market output, but we don't know the hidden input. So the problem is that let's say we are doing bond pricing, we are trying to find the known part is the market bond price, right? Unknown part is we are trying to solve for yield or YTN, right? So root finding equation that will be model price minus market price equal to 0. Let's say we are trying to do option pricing. Again, known is market option price, unknown we are solving for implied volatility. The actual price minus market price equal to 0, right? We'll try to that. Let's say we are trying to find your internal rate of return, right? Known is the cash flow. Unknown, we solve for discount rate. Root finding equation is net present value equal to 0, right? So these are the things we have to keep in mind when we are trying to do it, right? Similarly, portfolio optimization, you have target return, you target risk constraint. So unknown, we are solving for your Lagrange multiplier parameter. Root finding equation is the constraint error equal to 0, right? So the core idea is that in finance, we will definitely have different financial problems with different known things. And when we are trying to solve for unknown, right, uh, we have to make some root finding equations to solve a particular thing, right? So that is called root finding. Okay. So in this particular slide, what we are saying is the lesson is all about numerical methods used when we cannot solve an equation cleanly by algebra and quant finance. This is everywhere. You price something, calibrate a model, solve for yield, solve for implied volatility, solve optimization constraint. Many times the answer is not available directly, so we use algorithms. The two main algorithms in the lecture are bisection method. Main idea is keep cutting an interval in half until the root is trapped tightly. Next method is Newton-Raphson method, which is use tangent lines and derivation to jump quickly towards the root. Okay, so let's dig deeper, guys. Let's try to understand this. Okay, now we have the introduction, right? Introduction to root finding part here, right? So in this introduction, the overview root finding problems involve determining the value of variable x such that the given function is by x equal to 0. In finance, many valuation and optimization problems used to root finding when closed form analytical solutions are unavailable. I told you this in introduction part. So, meaning we are basically looking for the point where the function crosses the x-axis of x equal to 0. That is what we are trying to understand here. And why root finding is very, very important in finance. The simple idea is that financial models often lead to your nonlinear equation, right? That's the first part, right? And market observed quantities must be matched, right? Market observed quantities must be matched to your model outputs, right? So that is what we have here. Okay, financial models often lead to nonlinear equations. Market observed quantities must be matched by model outputs. Numerical algorithms are required to approximate the solution. Common financial application, bond pricing, solve for the yield that matches the observed bond price, option pricing, computing implied volatility from the Maxwell formula, internal rate of return, finding the discount rate that set NPV to 0. Key insight, root finding transforms your pricing and valuation problem into numerical equations. Accurate root finding is essential for reliable financial decisions, right? So that is what we should keep in mind. Okay. So with that, we move to your next part, which is concept and algorithm, right? See, I told you, right, we are studying a bisection method and a Newton-Raphson method, right? So bisection method is one of the simplest and most reliable root finding algorithm. It is based on the intermediate value theorem, IV theorem, right? We state that if a continuous function changes sign over interval AB, then a root must exist within that interval. And again, I told you in the introduction slide also, and I told you this in the previous topic or previous lesson also, that choose A and B such that function of A into function of B is less than or equal to 0, right? And then compute the midpoint M is equal to A plus B divided by 2, and then evaluate your FM. If FM is equal to 0, right, then M is a root. If FA into FM is less than 0, then set B is equal to M. If FM, FB less than 0, then set A is equal to M. Then keep repeating until your desired tolerance is achieved, right? So what we are doing is we are tightening the what you say, the interval, right? As we are moving ahead, we are tightening the interval, and by tightening the interval, we are trying to reach to a level that where root is kind of approximated, right? In finance, equations are generally more complicated. By finance needs your root finding because many financial models are non-linear. For example, bond price and yield have an inverse non-linear relationship, right? Bond price formula, we understand that your price is equal to summation of your T is equal to 1, right? T cash flow T 1 plus Y raised to power T, right? So price equals the sum of cash flow time T divided by 1 plus E raised to D. So if we know Y, finding T is easy, but if we know market price B and we want Y, then we solve for, right, summation T is equal to 1. Okay, this is your root finding. The financial connection here is areas such as bond markets, solve for yield from bond price, options, solve for implied volatility from market option price, corporate finance, solve for IRR from cash flows, risk management, calibrate your model parameters, market data, portfolio optimization, solve for parameters, uh, which kind of satisfy the constraint. Key point is root finding converts a finance problem into a numeric equation, right? And in this particular thing, bisection method, right? The bisection method is the safest and the simplest root finding method. It relies on the intermediate value theorem I told you. Okay, if a continuous function changes sign between 2 points A and B, then there must be at least one root between them. That condition is FA into FB less than 0. F of A times into F of B is less than 0. This means one value is positive and the other is negative. Let's say F2, right? Let's say F2 is equal to -1 and F3 is equal to 4. Then F2, F3 is equal to -1 to 4, to -4 less than 0. right? So a root must lie between 2 and 3, right? Bisection midpoint formula, m is equal to a plus b by 2. Okay, m equals a plus b divided by 2. Here m is the midpoint, and we check whether root lies your a comma m or n comma b, right? We keep the interval where the sign change exists. The algorithmic logic here is step one is what we do, we choose a and b such that fa, fe, b less than 0, pi, because root is bracketed. You compare the midpoint m is equal to a plus b by 2, split interval, evaluate fm, which is check sign, then keep the half the sign change, which is root remains, repeat, interval becomes smaller. So that's the whole objective, right? In financial intuition, imagine solving bond yield, which I told you, right? Which is you're trying to find out this somewhere between 5 and 7%. You check 6%, right? If the model price at 6% is still too high, you adjust interval, then check 6.5 and then 6.25 and so on, right? Bisection is like asking is the answer in the left half or the right half, right? Okay. All right. The root is always bracketed with a shrinking interval. Convergence is guaranteed for continuous functions. Then we get into your interval halving intuition. Basically, the diagram shows the curve crossing the x-axis. The root is where fx is equal to 0. The interval starts from a to b, and the midpoint is m. The important visual idea is when you have a, b, right? Okay, each iteration cut the search area by half. For example, suppose we start AB is equal to 2 and 3, right? Let's say starting AB equal to 2 and 3. First midpoint is what? M is equal to 2 plus P by 2, which is 2.5. So then maybe the root lies between 2 and 2.5. New interval is 2 and 2.5. Second midpoint is what? Second midpoint is 2 plus 2.5 divided by 2, 2.25. New interval keeps shrinking. Why this is reliable? Because bisection does not need any derivative. They only need sign. So strength is simple explanation, easy to code, stable, does not jump wildly, guaranteed, works, the function is continuous and sign change list. Slow interval halves each time, so converges linear. In this system, reliability matters. Slow but guaranteed method is often preferred as a fallback. Okay, that is what we try to understand. Then we get into bisection method, Python implementation. The slide shows the implementation logic. Basically, in this particular slide, right, the code is given, right? So that is, we all know. Okay. The example function given here is fx x cube minus 4x minus 9. So f of x equals x cube minus 4x minus 9, right? If you take the interval, right? So interval, we have taken 2 and 3, right? So f of 2, we check, we get minus 9. And f of 3, I check, I get 6, right? So f of 2, f of 3 equal to minus 9 into 6 equal to minus 54, which is less than 0, right? So therefore, a root lies between 2 and 3. So we are getting different symbols, right? F of 2 and f of 3, right? We are getting different symbols. So key insight is bisection trades speed for reliability in finance. If you use case is bond yield, why bisection is useful? Because stable even when cash flows are irregular, when IRR good when multiple cash flow signs create numerical difficulty, when implied volatility say fall back if Newton fails. This system useful when robustness is more important than speed, right? So bisection trades speed for reliability often use the benchmark fallback method, common in bond yield and IRR. So that is what we have. Then we get into Newton-Raphson, which is concept and iterative formula. The Newton-Raphson method is a fast and efficient root finding algorithm that uses both the function value and derivative to iteratively approximate the root of an equation. Given a function f(x), Newton-Raphson update is this. Right, Newton-Raphson is faster than bisection but it is less safe, right? It uses the function value and the derivative. The update formula is your xn plus 1 equals your xn minus f of xn divided by f prime of xn. Here, if you look at it, xn is current guess, n plus 1 next improved guess, fxn function value of current guess, f dash xn derivative slope at current guess. The intuition here is that look at the tangent line in current point, where does the tangent line hit the x-axis, use that as the next guess. That is why Newton can make very fast by derivative matters, because derivative tells the slope, right? So f dash x is equal to df by dx. So f prime of x, or derivative of f with respect to x. If the slope is steep and will be here, Newton works well, but if the slope is zero or unstable, Newton can fail, right? So keep that in mind. Choose an initial guess x naught, compute f xn and f dash xn, update the estimate using the Newton formula, repeat until convergence solve has been met. Use this tangent line to approximate the root, converges quadratically near the solution much faster than the bisection. Then we get into the next part, which is tangent-based convergence. Basically, diagram shows a curve and a tangent line at starting point x naught. Draw the tangent crosses the x-axis at x1, then form xi, repeat the same process. So basically what is happening, xo, then x1, then x2, then x3, then we are getting to root. Okay, so what is happening usually? Bisection says cut the interval in half, Newton says use the local slope to jump closer. That is why Newton is much faster and the initial guess is good. Financial example is implied volatility. Suppose market option price is 12, right? Black shows price depends on volatility. We have CBS, sigma minus C market is equal to 0. Newton update becomes sigma n plus 1 is equal to sigma n minus CBS, sigma n minus C market, vega, sigma n. Right, because the derivative of option price with respect to volatility is vega, sigma n plus 1 equals sigma n minus Black-Scholes price minus market price divided by vega. This is a very important quant finance use case. Please understand that, right? So very fast convergence near the root. Then we get into the next part, which is Newton-Raphson, how the method works. Basically, Newton-Raphson method. Again, this is kind of what we have discussed already. Newton-Raphson method is an iterative root finding algorithm that uses local linear approximation to rapidly converge to the root of the non-linear equation. Start with initial guess x naught, compute the next approximation, this one, repeat the update until the desired tallest is achieved. Each iteration uses the tangent at xn to approximate the root. Convergence is rapid when the initial guess is close to the true root. So slide kind of repeats the step-by-step procedure which we have seen earlier. Step 1, start with initial guess x naught. This could be anything, right? This could be a problem such as bond yield, where the initial guess is 5%. And it could be implied volatility where initial guess is 20%. It can be IRR where the initial guess is let's say 10%. And model calibration where the previous day's parameter has been taken. In real finance system, yesterday value is often a good starting point. Step 2 is apply Newton update, which is xn plus 1 is equal to xn minus fxn divided by f dash xn. Step 3, stop when error is small. A common stopping condition is what? A common stopping condition is your f of your xn, right, less than your epsilon, right? Absolute value of f of x n is less than your epsilon. Here, epsilon is the tolerance. For example, let's say your f of your xn is then 10 raised to the power minus 6, meaning the function is almost 0. The idea is Newton uses local linear approximation. That means it temporarily treats the curve like a straight line near the current point. It's very similar to using your first order expansion, which is fx f of xn f dash xn x minus xn. Set this approximation equal to 0. 0 is equal to f xn f dash xn x minus xn. Right, solve for x. X is equal to xn minus f your xn f dash xn. This is exactly the Newton formula which we are studying. Then we get into advantage and limitation. Advantages are, very fast convergence, quadratic convergence, high accuracy achieved with fewer iteration, efficient for smooth function with well-behaved derivatives, widely used for implied volatility in IRR calculations. Limitation requires availability of f dash x. Method fails if f dash x is 0 near the root. Sensitivity So the choice of initial case may diverge for poorly behaved function. Practical insight is often combined with bisection for robustness, used after bracketing the root safely, right? So basic idea here is the Newton-Raphson. Uh, when we look at advantage and limitation advantage, quadratic convergence, meaning error reduced very fast near the root, and fewer iteration usually needs fewer steps than bisection, efficient related for smooth function. Common in finance, used in implied volatility, IRR calculation. What does quadratic convergence mean? If the error is small, Newton roughly squares the error each uh, iteration. For example, 0.01, 0.0001, 0.00000001, right? This is extremely fast. Limitation here is that we need derivatives, right? We need derivatives which are f dash x, right? Sometimes derivative is hard to compute. Fails if f dash x is equal to 0. Division by 0 problem, sensitive to starting point, bad initial guess can diverge. Poorly behaved function can jump away from the root. So financial connection is in implied volatility. Let's say we have f, the sigma is equal to vega. Okay, if vega is very small, Newton becomes unstable. This can happen for deep in the money option. Why Newton may struggle because price not very sensitive to volatility. Deep out of money option, vega can be tiny. Near expiry option, vega collapse. In liquid option, market price may be noisy. That is why practitioners often combine Newton with bisection. Uh, Again, the next part is Newton-Raphson method, Python implementation. Again, the example again uses same concept, fx, or same example, x cube minus 4x minus 9 derivative, we take f dash x is equal to 3x squared minus 4. F prime of x equals 3x squared minus 4. The Python code is in front of you, and then basically this is Newton-Raphson in optimal pricing. X is in finance equivalent A is equal to sigma. Fx is pricing error. F dash x is vega. Root is implied volatility. So key insight is efficient numerical solver for non-linear equation commonly used in financial calibration problem. Then we get into the next part, which is basically your comparison bisection versus your Newton-Raphson method. This slide compares both methods, right? So again, you have your features and bisection method and Newton-Raphson method, right? So speed is slow in bisection, Newton-Raphson fast, convergence in bisection linear, Newton-Raphson quadratic, needs derivative in bisection no, Newton-Raphson yes, needs initial interval in bisection yes, Newton-Raphson no, needs initial guesses in bisection less sensitive, Newton-Raphson very sensitive, reliability very high in bisection, Newton-Raphson medium, failure risk bisection low, Newton-Raphson higher, finance use bisection is safe fallback, Newton-Raphson is fast production solver, and then when you compare your linear versus quadratic convergence, bisection reduces the interval by half. Error after each step is 1/2 almost. Newton can reduce error much faster. New error is your old error square, right? Almost in Newton-Raphson. New error approximately equal to old error square, right? So practical rule is if you need safety, better method is bisection. If you need a good starting point, better method is Newton. If you have a derivative variable, better method is Newton. If your function is messy, better method is bisection. If your function is messy, better method is bisection. If your production quant system, better method is hybrid. An hybrid approach, a common professional approach is use bisection to safely bracket the root, use Newton to converge quickly. If Newton jumps outside the interval, fall back to bisection. This gives speed and reliability. Okay, so bisection is preferred for robustness and guaranteed convergence. Newton-Raphson is preferred for speed. And a good initial guess is available. Hybrid methods combine both for efficiency and stability. Okay, so that is what we have. Then we get into the next part, which is the financial application. Root finding methods play a fundamental role in quantitative finance, where many valuation decision-making problems reduce to solving non-linear equations numerically. Key application: bond pricing, implied volatility, and option pricing, internal rate of return. Root finding is used to compute the bond yield by solving for the discount rate that equates the present value of the future cash flow to the absorbed bond price. Implied volatility is obtained by solving the Black-Scholes pricing equation for volatility such that the model price matches the market price. IRR is the discount rate and makes an NPV of future cash flow equal to zero and computed using numerical root finding algorithms. Key insight: many core financial quantities are not available in closed form. Root finding transform valuation problem into solvable numerical equation. Accuracy and conversion are critical for reliable financial decisions. This is one of the most important slides because this is connecting the maths to finance, right? Bond yield, the bond price we understand, right? So bond price, the equation is what? Price is equal to summation, T equal to 1 to T cash flow 1 plus your Y raised to power T. So if market price is known, solve for yield Y. And how do we solve for yield Y? We take summation, right? T is equal to 1 cash flow T 1 plus Y raised to power T minus price in the market equal to 0. This gives yield to maturity. Why root finding? Because yield appears inside the denominator and exponent. For multiple cash flow, solving directly is not easy. Then we have implied volatility. Again, Black-Scholes call price, right? Implied volatility, same. You have call price from Black-Scholes. You have the formula, your call price from the market. So you take call price from the Black-Scholes by the full equation you take for sigma minus call for the market, equate to 0. The unknown is sigma. This implied volatility. Why important? Because implied volatility is not directly observed. It is backed out from market prices. In option markets, implied volatility is often more important than the option price itself because it tells us what volatility the market is pricing, right? Then we have IRR, right? Same thing here also. NPV, we put NPV is equal to 0. And NPV calculation is what? The summation T is equal to 0. CFT 1 plus R raised to power T. Okay, sum of discounted cash flow equals 0 in finance. If application is bond yield, equation is price equation. If application is implied volatility, equation is Black-Scholes price error. If your application is RR, equation is NPV equation. If your application is model calibration, equation is market price, model price. Unknown parameter. If your application portfolio optimization equation is constraint equation, unknown is multiplier weight parameter, right? So keep that in mind. Okay. Then we get into next part, which is a summary, the key takeaways. In this lesson, we examine two fundamental numerical methods used to solve nonlinear equations in finance: the Bisection Method and the Newton-Raphson Method. Core concept used: root finding is a central problem in financial modeling, working problems for the Bisection and Newton-Raphson Method. Comparison of conversion speed, robustness, and implementation complexity, strength and limitation of each method in practical settings. The insight is Bisection provides guaranteed for slow convergence. Newton-Raphson offers fast convergence but requires good initial guesses. Method selection depends on accuracy, stability, and model behavior. Practical cases, we have discussed bond yield computation, implied volatility estimation, and your internal rate of return calculation, right? So the lecture summary is very clear. The concept, if you're looking at root finding, means solve fx is equal to 0. Bisection, slow but guaranteed method. Newton-Raphson, fast but needs derivative and good guesses. Finance relevance, bond yield, implied volatility, IRR. Practical choices depends on speed, accuracy, and robustness. Main takeaway here is that Bisection is like a safe search. Newton is like a smart jump. In real finance, we usually care about your requirements such as accuracy. If you're looking for accuracy, why it matters? Because if you have wrong route, means wrong price, yield volatility. If you're looking for stability, means this system must not fail randomly. If you're looking for speed, pricing, thousands of instruments need efficiency. Robustness, market data can be noisy. Slide also says these ideas later extend to optimization, feeding solvers, and simulation. That is true because many advanced numerical methods repeatedly solve equations, right? That is what we need to remember. Okay. Then we have question 1 to 3. Question number 1, again, root finding basis. Define a root mathematically. A root is a value x star such that f x star is equal to 0. X star is a root if f of x star equals 0. Here x star means the solution value to financial application is your application bond pricing, yield that matches the market price. Root being solved is the application option pricing, implied volatility that matches the market option price. Why analytical solutions may be unavailable? Because financial equations are often you're looking for non-linear bond pricing relation, complex Black-Scholes inversion probability, if you're looking for data-driven calibration to market pricing, if you're looking for multi-period IRR with many cash flows, right? So these are your analytical solutions, unavailable, right? Why many analytical solutions may be unavailable? Because financial equations are often non-linear, complex, data-driven, multi-period. Right? Non-linear means bond price yield relation. Complex such as Black-Scholes inversion probability. Data-driven because calibration to market price. Multi-period means that IRR with many cash flow. Okay. Then we have your question number 2. Bisection show that rule for fx equals to minus 5 in 2 and 3, right? Simple idea. Find out f2. Find out f3. F2 is -1, F3 is 4, right? So if you take F2, F3 is equal to -4 less than 0. So there is a sign change. The root exists in 2 and 3. Iteration, you can do more iteration, perform 2 iteration. M1 I can do 2 plus 3 by 2, right? Equal to 2.5. I can find F 2.5, which comes 1.25. So F2 less than 0, F 2.5 greater than 0. So root lies in 2 and 2.5, right? 2 and 2.5, the root lies, right? I can do again an iteration. I can take M2, 2 plus 2.5 divided by 2, which is 2.25, right? So F2 in this case, F2 less than 0, F2.25 less than greater than 0. Right, so root lies between 2 and 2.25. Actual root bisection is moving toward its safety, right? So that is the convergence happening. Question number 3, Newton-Raphson compute derivative of fx equal x3 minus 4x minus 9. That you know that, right? So if fx is equal to x cube minus 4x minus 9, f dash x is equal to 3x square minus 4. The slide solution seems to have a smile, kind of small typo, right? X1, if you look at, right, if you, you'll go ahead, right? So X1 is equal to 2 minus 1 by 8, right, is equal to 2.125, right? So, but for, if we kind of, fx, right? We'll see that in the next slide, right? Let's not see it here, right? So I'll show you in the solution, right? So basically, for question number 3 solution, we'll just look at one small typo, right? We'll try to remove that. Okay, so or we can see it right now, right? If you go here, right? So here, what is happening is the x1 is shown 2.125, right? But for fx is equal to x3 minus 4x minus 9. If you put f2, it is coming as your minus 9, not your minus 1. So the correct Newtonian calculation here will be x cube minus 4x minus 9 is iteration 1 will be x naught is equal to 2, f2 is equal to minus 9, and then f dash 2 is equal to 3 into 2 square minus 4, which will come out as 8. So x1 will be 2 minus 9, right, by 8, right? So it will come at 3.125, right? So this should be minus 9, right? This should be minus 9. Okay, so small typo, I have corrected it. This should be minus 9. Okay, solution is also here. And if I do iteration 2, right? If I do iteration 2, this will become 3.125. If I do iteration 2, f of 3.125, right, equal to 3.125 cube minus 4 into 3.125, right, and minus 9. So x2 will become your approximately equal to your 2.7686. 2.7686. So this is the correct answer, guys. 2.7686. Right. The root is around And X, you know, you know, if you kind of, and how did I get X to this one? Basically, X2 is equal to 3.125 minus 9.0176, right? Divided by your 25.2969. Right now, how did I get that? Basically, that was if when I put f of 3.125, I got 9.0176. If I when I did f of dash of 3.125, I got 25.2969. Right. So eventually, uh, H2 we have found 2.7686. Right. So again, right. So we need to keep that in mind very, very clearly. Okay. So conceptually, the slide is correct, right? You know, uh, that's not wrong, right? But the numerical numbers are a little wrong, right? Okay. So don't worry about small error, guys. I have corrected it, so don't worry about that. So start x naught is equal to perform two iterations. Okay. Then you have question number 4. Uh, you have method comparison, compare your convergence and robustness. Again, convergence, bisection, slow, linear, right? Newton is fast, quadratic. Robustness, bisection, very robust. Newton-Raphson, less robust. Uh, Initial guess sensitivity, bisection, low. Newton-Raphson, high. Derivative needed, bisection, no. Newton-Raphson, yes. Preferred for IRR, often Newton, but bisection is better. Newton-Raphson, fast, if initial guess is good. Preferred method for IRR, for standard cash flow, Newton is usually preferred because it is fast, but if cash flows are irregular, so there are multiple sign changes, IRR can have multiple roots. In that case, bisection or hybrid methods are safer, right? So that is what we have. And question number 5, financial application, bond yield, implied volatility, IRR. Even though we have solved in the slides itself, right? So bond yield that equates present value of cash flow to price, implied volatility makes Black-Scholes price equal market price. IRR is discounted and makes NP equal to 0. Common structure is model output minus your observed target output is equal to 0, right? So that is what we have. So solutions are there. All solutions are perfectly correct, guys. Only small error in this solution, I have corrected it, right? And that you can see. Otherwise, we are done with this lecture. Quite interesting topic. A new kind of methodology which you should see, understand. Uh, they are used in your yield, can affect your bond price, duration, hedging. It is used in your implied volatility, can affect your option valuation base. It is used in IRR, affect your investment decision, calibration parameter, risk numbers, and profit and loss attribution. For example, if implied volatility is wrong, then delta, gamma, vega, var, hedging decision, and risk reports can all become wrong. And the full mental model, if you have to understand, root finding is not just a math trick, it's a core engine behind valuation calibration. If fx equals 0, simple meaning is find where that function equals 0. Bisection, safe, interval shrinking, Newton-Raphson, tangent base, fast solver, tolerance, how fast is close enough. Convergence is about whether method reaches answer or not, right? So if concept is your fx is equal to 0, when I say that find where function equals 0, it is about finding your input that matches your market output. When I say bisection, safe interval shrinking, it means robust solver. If concept is Newton-Raphson, simple meaning is tangent based, fast solver means fast calibration pricing solver. If your concept is tolerance, simple meaning how close is close enough, pricing or the risk accuracy standard. If the concept is convergence, simple meaning is whether method reaches answer or not, the model is usable in production or not. The most important line to remember here is that root finding solves your model input minus market input is 0, which I wrote in the one slide also, right? So that is why this topic is very, very foundational for bond yield, implied volatility, IRR, calibration, risk management, and portfolio optimization, right? So keep that in mind, guys. Okay. That's it, guys. That's it for this chapter. I'll see you in the next chapter. Go back, revise it till that time. Uh, solve these questions, right? So at least do it twice, you'll be totally fine. And once you've done it, I think that's great. Okay. All right, guys. Thank you.